We continue with lecture 26 about partial differential equations. So we have the heat equation, U sub T equals alpha squared U sub XX with boundary conditions, U sub 0T, U sub U of 0T, U of L of T are both 0. So when you consider only this boundary value problem, this has solutions U given as an infinite sum n from 1 to infinity Cn e to the power minus n squared pi squared alpha squared t over L squared sine of n pi x over L. But remember, we also have the initial condition. U of x0 at time t equals 0, the heat distribution is given by the function f. Now, if we use this, in this sum, if you put t equals 0, n from 1 to infinity, Cn, when you put t equals 0, e to the power 0 becomes 1. So that term disappears. We have sine of n pi x over L. So then given this function f of x, can we find the constant Cn, infinitely many, so that our function is equal to this infinite sum? Such a series is called a Fourier Sine series. We obtained a sine function because of the boundary conditions. If you have different boundary conditions, you may get different functions here. Instead of sine, you may have cosine, or you may have both, depending on the boundary conditions. But for this particular boundary conditions, we get the sine function. So now we consider this problem about, given this function, can we always find the constants Cn? So to answer this question, first we consider periodic functions. So a function f of x is called periodic with period t if f of x plus t is equal to f of x. This is the usual definition of period. The thing to be careful about is that if t is a period of f, then all multiples of t are also a period. Then 2t, 3t, all multiples of nt are also periods. Of f. Consider sine, cosine. They have period 2 pi, but 4 pi, 6 pi, 8 pi, they are also periods. For sine and cosine functions, especially like the sine function in our series, if you have sine n pi x over L or cosine n pi x over L are periodic with period, not 2 pi, because pi is already in the argument. Because of this L in the denominator, we get the period 2L. If you consider sine of n pi x plus what is happening again? X plus 2L divided by L. This is sine of n pi x over L plus 2n pi. But we know that 2 pi and 2n pi is a period of sine. So this is same as sine of n pi x over L. So 2L is a period, same for the cosine function. So these functions are periodic with period 2L. So we have this theorem called Fourier Convergence theorem. Suppose f of x is a piecewise continuous function. You know the definition of piecewise continuous. When we consider Laplace transforms, we consider piecewise continuous functions. So they have points of discontinuities, but in any finite interval, there are finitely many discontinuities. And at the discontinuities, we have left and right limits. They may not be equal, so the function is bounded, but it may have a jump discontinuity at some points. So piecewise continuous function of period 2L. I'm sorry. Okay. Then there is a unique set of constants. We have two groups of constants, A's, A0, A1, A2, infinitely many, and B's. B starts from B1, B2, such that we can write our function f as, this is like a power series, but instead of powers of x, we are going to have sine and cosine. So first we have the constant term, A0 over 2, plus an infinite sum with the cosine function, cosine n pi x over L. And then we have another sum with the sine function, bn sine n pi x over L. For every x where f is continuous. So we get this Fourier series. These are called Fourier sine and cosine series. We get the Fourier series for the function at points where it is continuous. At the discontinuities, again, it cannot be just anything. We have a certain behavior at discontinuities. If the function f is discontinuous at x, let f x minus be the limit at x0, let's say, x0 minus be limit as x goes to x0 from left of f of x. Remember, since it's piecewise continuous, this limit must exist, and x0 right limit as x goes to x0 from right of f. Again, this is a real number. This definition of piecewise continuous. Then at this point x0, when you write this series, so for x, you put x0, bn, it converges, the series converges, but since f has different limits on the right and on the left, this converges to the average of the two numbers. Okay, so you may have at the point x0, you have x, f of x0 can be anything, but let's say this number is f x0 minus, and let's say this number is f x0 plus. Okay, then this series converges to the average of the two numbers. Okay, f of x0 can be anything. We don't care. But at the points where f is continuous, the series converges to f of x. Okay. This theorem is a deep theorem, and the proof is beyond the scope of this course. So we are going to skip the proof. We are not going to give the proof here, but we are going to consider the question how to find ANs and BNs. Given this function f satisfying the conditions of the theorem, we know that those constants exist. How do we find them? For that, we use a very handy property of trigonometric functions, orthogonality. Those of you who have taken a linear algebra course may be familiar with the term. So in order to talk about orthogonality, first we need to talk about an inner product. We are not going to go into the linear algebraic details, but just give you the definition. So for piecewise continuous functions, fx and gx with period 2L. So both of them must have the same period, 2L. Their inner product, of course, you can define many different inner products for functions, but the most commonly used is this inner product. We define it by an integral. So inner product, we denote it with this parentheses, f and g. It is defined to be the integral from minus L to L of their usual product. Okay, so minus LL is just, so since the period is 2L, you can take basically any interval of length 2L. But taking an interval like this is going to be convenient when we consider sine and cosine functions. Because sine function is an odd function and cosine function is an even function. So it is also true. Okay, so when you consider this interval minus L for the sine function, it is going to be like this. Wait. 0 to 2 pi minus pi minus pi, yeah, something like this, right? For the sine function, odd function, and for the cosine, it is going to be okay, let's take a different color for the cosine. It is going to be something like this, right? For the cosine. Cosine is an even function and sine is an odd function. But instead of having the interval minus L to L, if you take any interval and consider the midpoint, with respect to the midpoint, the graphs of sine and cosine, again, behave in the same way. So, of course, for any piecewise continuous function with period 2 pi, it doesn't have to be even or odd. So the Fourier sine series, in a way, gives the odd part of your function, and the Fourier cosine series gives the even part of your function. Okay, but back to the inner product. So we consider this integral from minus L to L. So this inner product satisfies maybe this is y equals sine to n pi x over okay, and here I'm taking n equals 1, so sine of pi x over L. N gives you the number of waves in the interval minus L to L. When n equals 1, you have only one wave. If you take n equals 2, in the same length, you will have 2 waves. For n equals 3, you will have 3 waves, and so on. And for cosine, same thing. Cosine pi x over L. Okay. So back to the inner product. This inner product satisfies. First of all, if you interchange the order of the functions, you get the same thing, because inside the integral, order of multiplication is not important. Also, if you take a sum in one of the functions, you can distribute inner product over the sum. Because inside the integral, for f, if you take f1 plus f2, you can distribute f1g plus f2g, and you can distribute the integral over the sum. And if you take a constant, if you multiply the function f with a constant, you can take the constant out, because you can take the constants out of the integrals. Okay, now what we are going to do, we will compute this inner product for sine and cosine functions. So inner product of sine n pi x over L. Okay, n pi x, and again sine of m pi x for different n or same different values of n and m. You can take the sine function with the cosine function, or you can take two cosine functions. But to compute, it means we take the product and integrate from minus L to L. To do this, we need some trig identities. We need the trigonometric identities. If you take a sine of A times sine of B, you can write this as 1/2 cosine of A minus B minus cosine of A plus B. You can check using the addition formula for cosine that this is true. If we have cosine of A times cosine of B, then instead of minus, we take plus in between. And if you have sine A cosine B, then you use addition formula for sine. Sine of A plus B plus sine of A minus B. You can check that these identities are true. Okay. Also, observe that for n different from 0, if you take n different from 0, the integral from minus L to L of sine n pi x over L. This integral is easy to compute. Antiderivative of sine is a minus cosine, and we need to divide by n pi over L. So L over n pi minus cosine of n pi x over L from minus L to L. But you see, if you put x equals L or x equals minus L, cosine is going to give you the same thing. So the result is going to be 0. Same thing for sine, for cosine. L over n pi sine of n pi x over L minus L to L. And for sine function, when you put L or minus L, the result, both of them are going to be 0. So this integral is also going to be 0. Okay, so we are going to use all of these to compute the inner product of sine and cosine functions. Okay, so keep these in mind. Now, let's say I want to compute the inner product of sine n pi x over L sine m pi x over L. So this is the integral from minus L to L sine of n pi x over L sine of m pi x over L dx. So this is like sine A, sine B. And by the trig identities, this is equal to 1/2 cosine of A minus B. So n minus m pi x over L minus cosine of A plus B. So cosine n plus m pi x over L. Okay. So if we separate, here, this is for sine. Remember, in the Fourier series, the coefficients of sine, let's see, where it starts from 1. So n starts from 1. N and m here are both greater than or equal to 1, because if they are 0, then if n or m is 0, one of them is 0, the whole thing is 0. So n and m are both greater than or equal to 1. Now, for these integrals, remember, integral of cosine something pi x over L from minus L to L, this is 0. This is 0 if n minus m is different from 0. And similarly, this is 0 if n plus m is different from 0. But since n is greater than or equal to 1, m is greater than or equal to 1, we have n plus m always different from 0. So the second integral is always going to be 0. We are going to have only the first integral for n minus m equal to 0. So n minus m equal to 0, that means n equals m. And in this case, the integral is equal to, so sine n pi x. With itself is going to be 1/2 integral from minus L to L. When n minus m is 0, this whole thing is going to be 0, but cosine of 0 is 1. And this integral is 2L divided by 2. The value is going to be L. So this inner product is going to be L if n is equal to m, and 0 if n different from m. And remember, n and m are greater than or equal to 1. Okay, now how about cosines? So this is one result. Now, same thing with cosines. But the thing to keep in mind here is that now for cosines, we can take n and m to be 0, because cosine of 0 is not 0, it is 1. So we need to be a little bit careful. But the same thing here, the definition is the integral from minus L to L, cosine of n pi x over L, cosine m pi x over L. So using the addition formula, we can write it as 1/2 the integral. Let's see, how do we write the cosine? A times cosine b, cosine of a minus b, so cosine n minus m pi x over L, plus cosine of n plus m pi x over L. So same thing, this is 0 for n minus m different from 0. And this is 0 for n plus m different from 0. So we need to consider the cases when n minus m and m plus m equal to 0. So n plus m is 0 if and only if both of them are 0. Right? So if both of them are 0, then n minus m is also 0. So we have, in this case, if both of them are 0, cosine 0 is 1. We have inner product of 1 with itself, right? So this is the integral from minus L to L of the constant function 1. So in this case, the integral is 2L. Or by this formula, when both of them are 0, this integral is going to be 2L. This is 2L plus 2L plus 2L. 4L times 1/2 is going to be 2L. So inner product of 1 and 1 is going to be 2L. But if one of them is not 0, then m plus m cannot be 0. So for n minus m equal to 0, but m plus m is not 0, meaning both of them are greater than 0. One of them greater than 0 is enough. But m minus m is 0, so n equals m. So both of them are positive. Then the integral, so cosine n pi x over L, cosine n pi x over L. In integral, we have 1/2 integral from minus L to L, cosine 0 is 1, plus the second integral is going to be 0. So this is going to be L. So this inner product we have 3 cases. It's going to be 2L if both n and m are 0. It's going to be L if n is equal to m but greater than 0. And it's going to be 0 if otherwise in all the other cases. Maybe I should give them names. Let's call this equation 2. Above, we have same thing for sine. So let's call this 1. Now we get 3 from inner product of sine and cosine. Oops. Here, n is greater than or equal to 1, but m may be 0. Okay, by definition, this is the integral from minus L to L of the product. By the addition formula for sine, we can write this product as, let's see, when we have sine and cosine, we can write it as sine of a plus b plus sine of a minus b. So sine of n plus m pi x over L and sine of n minus m pi x over L. So again, it is 0 if n plus m is different from 0, and this is 0 if n minus m is different from if n minus m different from 0. Now, since n is always greater than or equal to 1, we have n plus m always positive. So the first integral is always 0. If n is equal to m, then inner product, let me not write the same thing, inner product is equal to, again, L. The second integral, oh, wait. No, okay, let's see. If n minus m is 0, if n minus m is 0, then sine 0 is 0. So the second integral is also 0. So this integral is always going to be 0, even if n is equal to m, because sine 0 is 0. So this inner product is 0. Okay, this is equation number 3. Okay, now we are trying to write a function. F is a piecewise continuous function with period 2 pi. We are trying to write it as some number a0 over 2 plus an infinite sum an cosine n pi x over L plus sum n from 1 to infinity bn sine of n pi x over L. So to find the constants, we are just going to take the inner product of the function f of x with sine and cosines. So if you take its inner product with cosine of n pi x over L, n greater than or equal to, here n maybe oh, yes, okay, n greater than or equal to 0. So this inner product, instead of f, we are going to put this expression here. Okay, let me say put this as m, because we have n's for f. Okay, so we have a0 over 2, inner product of 1 with cosine m pi x over L, plus the sum n from 1 to infinity an times inner product of cosine n pi x over L with cosine m pi x over L, plus an infinite sum n from 1 to infinity bn inner product of sine n pi x over L with cosine m pi x over L. Okay, for inner product of sine and cosine, we know that it is always 0. Inner product of cosine m pi x, cosine m pi x, it is equal to, what is it equal to? It is equal to 2L if both of them are 0, but n starts from 1. Even if m is 0, n cannot be 0. So this case cannot happen. If n is equal to m, it is L, is equal to L. if n is equal to m. Both of them cannot be 0. All right? So we consider the cases m is 0 or not 0. So if in the first inner product, this 1 we can write as cosine of 0 pi x over L. Okay, so for this inner product, when m is 0, we get 2L. All right, so this is equal to, all right, if m is equal to 0, all right, from this infinite sum, the first infinite sum, we don't get anything because n starts from 1. If m is 0, they can never be equal. But from the very first inner product, cosine of 0, this inner product is going to be 2L times A0 over 2. It's going to be A0 times L. And if m is greater than 0, then for the first inner product, we get 0 because m is not 0. The first one is going to be 0. In the second one, we get L only when n is m. So in this infinite sum, we get the number L when n is equal to m. So we have am times L. But in either case, it is am times L. Okay, for m greater than or equal to 0. So the constant, so this tells me that the constant a sub m is 1 over L times the inner product of the function f times cosine m pi x over L. Or changing m to n, an is 1 over L, inner product of f of x times cosine n pi x over L. This is for n greater than or equal to 0. Yes. Similarly, I'm not going to go through the same thing, but similarly, b sub n is going to be 1 over L, inner product of f with sine n pi x over L for n greater than or equal to 1. Okay. So before I finish this video, let me just give you one example. Without an example, it wouldn't be complete. So let's take a periodic function. Suppose the function f of x is equal to 1 for x between 0 and 2. It is equal to minus 1 for x between minus 2 and 0. And f is periodic with period 4. We are given the function for x between 0 and 2 to be 1. And from minus 2 to 0 to be minus 1. It doesn't matter what happens at 0, plus 2 and minus 2, because the important thing is the intervals. And then it has period 4. So after this, it's going to repeat the same picture. And so on. So it is periodic with period 2 pi. So the picture from minus 2 to 2 is going to repeat itself. Okay. let's find the Fourier coefficients of f. Okay, so we need to consider first inner product with cosine of n pi x over what is L? L here is 2. Period is 4. Remember, period is equal to 2L. So L is equal to 2. So we this integral is equal to from minus 2 to 2. Remember, from minus L to L. The function f times cosine n pi x over 2. Now, from minus 2 to 2, we divide it into two pieces. From minus 2 to 0, our function is minus 1. So minus cosine. And from 0 to 2, the function is plus 1. But since cosine is an even function, the integral from 0 to 2 is going to be the same as the integral from minus 2 to 0. So integral from minus 2 to 0 of cosine n pi x over 2 is equal to the integral from 0 to 2. So this inner product is going to be 0. Okay. You can also think of it this way. You can see that f is an odd function. For negative x, f of negative x is negative of f of x. F is an odd function. So we don't expect any cosine part in the Fourier series because cosine is an even function, but f is an odd function. So finding the coefficients of cosine, so all an's are 0. On the other hand, if you look at the inner product with sine, again from minus 2 to 2, f times sine n pi x over 2, minus 2 to 2. So minus 2 to 0, the function is minus 1. And then from 0 to 2, the function is plus 1. But now sine is an odd function, so integral from minus 2 to 0 of sine n pi x over 2 is negative of the integral from 0 to 2, because sine is an odd function. So this inner product is twice the integral from 0 to 2 sine n pi x over 2. Ni derivative of sine is minus cosine, so we have minus 2. Coefficient of x n pi over 2, so 2 over n pi cosine n pi x over 2, x from 0 to 2. When you put x equals 2, so minus 4 over n pi, when you put x equals 2, we have cosine of n pi. Minus, when we put x equals 0, cosine of 0 is 1. Now, what is cosine of n pi? It depends whether, and here n is greater than or equal to 1, remember. It depends whether n is an even integer or an odd integer. Now, cosine of n pi is 1 if n is even, and -1 if n is odd, right? Okay, so in this inner product, cosine of n pi, we subtract 1. So cosine of n pi -1 is 0 if n is even, and -2 if n is odd. So if we write n odd 2k plus 1, then inner product of f with sine of 2k plus 1 pi x over 2 is going to be, this side is -2, 8 over n pi. Wait. Right? Because this is -2 if n is 2k plus 1. So -2 minus 4, 8 over n pi. So the coefficient, okay, so the coefficient bn is going to be 0 if n is even. And remember, for bn, we take 1 over L times the inner product. So it is 1/2 of this inner product. We take 1/2. So instead of 8, we have 4 over n pi if n is odd. Okay? So the function f of x is equal to, then, for odd n, we take n equals 2k plus 1. K starts from 0, right? Because k equals 0 gives n equals 1. So this is the sum, k from 0 to infinity, 4 over 2k plus 1 pi sine of 2k plus 1 pi x over 2. So for k equals 0, we have a 4 over pi sine of pi x over 2. For k equals 1, we have a 4 over 3 pi times sine 3 pi x over 2. For k equals 2, 4 over 5 pi sine of 5 pi x over 2. So it's an infinite sum like this. Okay. All right, so if we have a piecewise continuous periodic function with period 2L, by taking the integral of f times sine and cosine of the appropriate function, of the appropriate argument, we can find the Fourier coefficients and write our function as a Fourier series. And now we need to use this in the heat equation case. Remember, we find solutions, and for the initial condition, the initial heat distribution given by the function f, we need to find the solution. And to find the solution, we are going to use this Fourier series. So in the next lecture, I'm going to consider special examples. It depends on the initial condition function, f of x. So also, I will try to include different equations, different partial differential equations, which leads to different Fourier series solutions, different boundary conditions, different initial conditions, gives you different Fourier series. I will try to prepare as many different types of examples as possible and show you how to combine the Fourier series together with separation of variables to find solutions of some partial differential equations. Okay, so that's all for now.